Now that we've gone over the formulas, now we can look at some questions. For example, here's a geometric probability question. There are 81 grid points in the square shown in the diagram, including the points on the edges. Point P is the center of the square. Given that point Q is randomly chosen among the other 80 points, what is the probability that the line PQ is a line of symmetry for the square? A, 1 over 5, B, 1 over 4, C, 2 over 5, D, 9 over 20, and E, 1 over 2. The solution is, as per the introduction in the geometric probability, we know that the probability formula is measure of the geometric figure representing the desired outcomes in the event over the measure of the geometric figure representing all of the outcomes in the same space. So this is a pretty typical geometric probability question that you will see in math contests. So first, we can find the desired outcomes in the event by randomly picking a point that can form a straight line with point P. As you can see in the solution diagram, there are 32 points that can be connected with point P to form a straight line of symmetry for the square. Secondly, to find all outcomes in this question, it's all 80 points. So as the total probability per formula is number of points that can form a straight line of symmetry with point P over the total number of points, which is 32 over 80, which is 2 over 5. So the answer is C. Here's another question. From a regular octagon, a triangle is formed by connecting 3 randomly chosen vertices of the octagon. What is the probability that at least one of the sides of the triangle is also a side of the octagon? A, 2 over 7, B, 5 over 42, C, 11 over 14, D, 5 over 7, and E, 6 over 7. So here we have two cases. Case 1 is that 2 points are adjacent as shown in the diagram, or 3 points are adjacent, which is shown in the other diagram. Alright, so our goal here is to connect 3 random points to form a triangle where at least one side is also a side of the octagon. Let us find the expected outcomes of the event. So for case 1, the triangle and the octagon should share one side with 2 points adjacent as listed in the 2 adjacent points diagram. In this case, each side, for example, point 8 and point 1, can be connected with 4 potential points which can form 4 potential triangles with point A and point 1 shared between the triangles and the octagon. If one side can be connected with 4 points, there are 8 sides in an octagon, so in total there are 32 points that can be connected to form triangles that share at least one side with the octagon. For case 2, the triangle and the octagon share 2 sides with 3 points adjacent as shown in the 3-point adjacent figure. So in this case, every 2 adjacent sides with 3 points of the octagon can be connected to form a triangle that shares 2 sides with the octagon. There are 8 points that can be connected to form triangles that share 2 sides with the octagon, as you can see in the dotted lines of the figure. So to sum up case 1 and case 2, we can add both of them together, which is 40 points that can be connected to form triangles that share at least one side with the octagon. So the total points that can form triangles are the 3 points that are randomly selected from the 8 vertices of the octagon, which is 56 points. So the probability of connecting 3 random points to form a triangle where at least one side is also a side of the octagon is 40 divided by 6, which is D5 over 7.